Okay, so we are ready to resume our activities. Our next talk is by Will Cortiñas and surprise talk. So let's see.
Yeah, Ruth was insisting that I should, uh, that he wanted to give less talks than he was assigned, and that if I could step in and give a talk. So I want to give some more details about what I talked about yesterday uh, at a little slower pace. So recall that this is the universal nice homology theory, and that I had stated this result that we have with Diego Montero, that if I will write the specific particular case, if E and F are finite regular, then an isomorphism. So an isomorphism between their Bauer-Franz groups implies that they are isomorphic in KK. So after applying J. So in other words, if E and F are finite regular graphs with isomorphic Bauer-Franz groups, there is no nice homology theory that can distinguish them, because any such theory would factor through J, and upon applying J, they become isomorphic. Uh, okay, but what I announced was that if E and F, apart from being regular, are SPI graphs, which implies that they're regular, then we could conclude that LE and LF not only were isomorphic in KK, but that they were homotopy equivalent. And I need, therefore, to investigate what extra property do SPI graphs have, apart that more specific than just being regular, which they are. Okay, and so I mentioned yesterday that if uh, E is SPI, then the Leavitt path algebra of E is PI, which means that there exist sequences of elements in LE such that TISJ is delta Ij. In other words, this means that if you call S the matrix, the row matrix whose elements are the Sn, and T the column matrix whose elements are the T's, then when you do TS, you get the identity matrix, the infinite identity matrix. Observe that it follows that if I truncate S and T, then TS, T less than N, S less than N, is nothing but the n by n identity matrix. Okay? And so ST is this product. So how much is this? Can anyone tell me? So I multiply these two matrices, this gives me this. What about the other product? I'm not expecting you to say it's 4 or it's something. What I'm expecting you to say is it's not defined. Why? Because what is this? This is the sum over all n of Sn Tn. It's an infinite sum. It's not defined in any algebra, right? If we were in an algebra with some metric, we could wonder whether this sum converges. But we do not have any metric, any norm or anything, so this does not exist. However, however, if you have, so recall M infinity is the union of the MNs, where an M by N matrix is regarded as an infinite matrix supported in the square in the first n rows and n columns, right? Which you add zeros at the end. Okay. Now, if you have an element A in here, then it will be in some n, right? And when you do, if I do S times A, it doesn't matter that this is infinite, because A will only have finitely many rows. Say if it has n rows, then this is the same as this. Yeah? And so if I have, this is R, I have an element A, I can map it, it makes sense, this is defined, to map it here. Because any A is in M infinity is finite. Right? And this is an algebraic homomorphism. Why? Well, so say, where does AB go? Where it goes here. And what about, so if I do S times A times T times S times B times T, then this is identity. So this is the same as this. Product goes to product. Aha. So suppose that your A is called P, which, as everybody knows, makes it idempotent. So say you have P and idempotent in M infinity. So I will call this idem infinity of R. Then, well, this P will be in some idem N of R for some finite number N. Right? We will have some size. And so S, P, T will be the same as S smaller than N times P times T smaller than N. Right? And look, call this X, call this Y. And then what do we have? XY is this. And what is YX? YX is P t less than or equal than n times s less than or equal than n. But this product is the n by n identity matrix, and P was n by n, so this is P. In conclusion, SPT and P are more von Neumann equivalent. So this says that if R is Pi, then any idempotent matrix of any finite size is more von Neumann equivalent to an idempotent of the ring. Right? So when you do the V monoid, you do not need idempotent matrices of any size. You just need one by one matrices. Moreover, what happens with the sum? So say we have P and Q idempotent matrices, one by one idempotent matrices, then, I mean, in VR, the one we all know, the matrix one, the sum is given by the direct sum matrix, right? But, so if I do S equal to this, and T equal to, so this will be equivalent to, so this is the sum in VR, right? And what is this? This is S1P T1 plus S2Q T2. Right? So the sum corresponds to a sum, and okay, so what I'm trying to say is that we have infinity, well, sorry, to emphasize the size of the matrices, I write as a index. So B infinity means the monoid of idempotent matrices modulo Murray von Neumann equivalence, right? One can also consider the monoid of idempotents modulo Murray von Neumann equivalence, and this map here, which I would call it R is T, because it's like an interior or homomorphism. This add ST induces an isomorphism here. I mean, yeah. So I didn't quite do the whole proof, but you can guess it from what I wrote. Okay. Right. So this is a good thing. And moreover, we can be, I mean, we're interested in the K0 of a properly infinite ring or Pi ring, and in particular in the case when the Pi ring in question is the Leavitt path algebra of some SPI graph. So let's some language. We have P and Q in R, idempotent. We say that P is bigger than Q if P can be written as P1 plus Q with P1Q equal QP1 equals 0. This automatically implies that P1 is also idempotent. And if you think of idempotent linear endomorphisms of some vector space, then this means that the image of P decomposes as a direct sum of the image of P1 and the image of Q. So in a sense, that Q is smaller than P means that it corresponds to the direct summand of P, right? Okay, and we write P than Q if there exists a Q1 Murray von Neumann equivalent to Q, so that P is bigger than Q1. Okay? And we say that P, a 1-by-1 idempotent matrix, is very full if P is than 1. So notice that if P is a 1-by-1 idempotent, then P is smaller than 1. Why? Well, because you can write 1 as P plus 1 minus P. And the fact that P is an idempotent tells us that the product of this and this in any of the two possible ways is 0. Right. So this is a special property, a strong requirement. But let us see what we have here. We said that if R is Pi, then we have this S and this T, right? And the n by n identity matrix is TS, and ST is some idempotent which lives in where does it live? In R, right? So, for example, the 2-by-2 identity matrix, regarded as an element in M infinity of R, is equivalent to this S1T1 plus S2T2 using this. And this is, well, it's a 1-by-1 idempotent, so it's smaller than 1. So we come to the conclusion that 2 is smaller than 1. This is 2. So my career in advertisement finishes here. I'm not going to be like Ken Ono. If you watch the Miller Draft beer commercial, whose the protagonist is Ken Ono. If you haven't, look it up in renowned mathematician Ken Ono. Anyway, so now you may say that this is intended to be a joke, just in case. The other day I said this, right? First lecture. So that it was good it was a good property that a ring with involution may or may not have, that in that ring -1 is bigger than 0. Now you might want to deduce this from this by adding 2, but that's very wrong. Okay? Okay. Right. So, and what happens is that if R is Pi, then suppose R is Pi, then consider VBF R to be the 1-by-1 idempotent matrices that are BF. Did I define BF? Or I forgot? Yes, here. This is BF. Okay. Modulo Murray von Neumann equivalence. So one can show that if you have an idempotent that is Murray von Neumann equivalent to one that is BF, then the idempotent is itself BF, And this follows from the fact that in here, I mean, this is clearly, if P and P prime are equivalent, then P prime is also satisfies this, because this is defined in terms of the existence of an equivalence relation, right? Of Murray-von equivalence. Okay, and okay, so this maps to V of R, to V1 of R, right? And moreover, so this map is a semigroup map. So what is the addition here is this, given by this formula, right? And if you have two VF things, P and Q are VF, and you do this, then this is still VF. This is what I mean by this being a semigroup map. But moreover, this guy has a zero element, which does not, so here the zero element is the class of the zero idempotent. The zero idempotent clearly is not VF, because the only idempotent that is Murray fundamental equivalent to zero is zero itself. A zero is not bigger than one. So, and who is the neutral element? Is the class of 1 minus S1T1, for example. So this, what property does this guy have? Well, you see, S1T1, the class of S1T1 plus nu is the class of 1, right? But S1T1 is in the same Murray von Neumann class as T1S1. And T1S1 is 1. Right? So this gives you an indication of, I mean, it doesn't prove anything, but it gives an indication of why this nu might be actually the neutral element, right? So, moreover, what happens is the following. So we have BBF, which maps, so this is semigroup map. So semigroup is like a monoid, but I don't ask that it has a neutral element, right? And then goes to V1R. And from here, I also have a map to BBFR. And that sends the class of P to the class of P plus nu. This is the identity. And this map, so theorem, so to speak, this map is the group completion. So what do I mean by that? What I mean is that BBF of R is the group completion of this, that is this, which by what we said is K0, right? So this is B infinity R plus, which is K0 of R. And, well, The group completion, the definition of group completion is it's a group, an abelian group, together with a map from the monoid to the group that is initial among all such maps. So what I'm saying is that this map has this universal property, right? And so that map, if we have a group G, then there exists a unique here that makes the diagram commute, right? So, yeah. Yeah. So this, you can look it up in Blackadar's book. On K-theory and operator algebras. In the particular case when R is purely infinite simple, every non-zero idempotent is very full. And this becomes a result of, so, case R SPI. This is a theorem of Ara, Goodell, and Pardo. So in this case, B1R is BBFR union 0. Okay. So why is this? Why is it important that that one can represent? So therefore any K0 class of a PI ring can be represented by a very full idempotent, right? So right. So now we recall also that for E finite and say RK1 regular, which implied KHI is KI R or I less than equal to 1, that we have an exact sequence KK of LE R goes to home BFE K0 bar. And here we have BF dual of E tensor K1 of R. Right? So this is the evaluation map. And what we have just, yeah. Okay, this is the evaluation map. And I want to say, this is the theorem that I announced the other day, yesterday, that every element here comes from a homomorphism. And that two are the same if they are M2 homotopic, right? So to begin showing that, the first thing I need to do is that anything here comes from somebody here. Okay? So what I want is the theorem which is partly in our paper with Montero, that suppose you have XC here, a homomorphism from here to here, where R is PI. I think K0 regular suffices for this, but say K1 regular. Or maybe I even don't need it. Yeah, RPI. R is PI. Then, and say that the class of 1, so think that this is BBF of R, right? So the class of 1E will go to the class of some P, which is BF idempotent. Right? So then there exists phi from LE to R, an algebra homomorphism, such that, well, when you do ebb phi, so that is when you do when you do that ebb phi is Xi. And what is ebb phi? So I go from BFE to K0 of LE via the canonical map. Then I apply K0 of Xi of phi, get to K0 of R, and this is Xi, and phi of 1 is P. So I want, moreover, I wanted to lift it to somebody here, right? This BF means homomorphisms that send one to a BF idempotent. It will always go to an idempotent. I want the idempotent to be very full. And this is telling me that so there is a map here. I don't know if it's surjective or not, but this theorem tells me that I do have a surjection here. Okay? So how does one prove such a thing? So proof. So the first thing is, so suppose, so the main thing is that this holds. And once you have one that satisfies this, then you can modify it slightly so that it also satisfies this. This is the first thing I'm going to say, I'm going to show. So suppose we have phi from LE to R, so that K0 phi composed with CAN is Xi. Right? So this is that this diagram commutes. Okay? Okay. Then the class of phi of 1 is Xi of the class of 1, and this is the class of P. Right? So this means that there exists an X in phi of 1 R P and a Y in P R phi of 1, so that X phi is phi of 1 and YX is P. Okay. And now define phi tilde from LE to R by phi tilde of A equal to, let me see, yeah. Y phi of A X. Then this new homomorphism, this new guy is still an algebra homomorphism and satisfies that phi tilde 1 is actually P. So how is this? Well, again, phi of A B is this, which is this. And now 1 is the identity of the source ring. right? So this is the same as phi of A, phi of 1, phi of B, right? Because when I multiply, I get AB, A1B is AB. And phi of 1 is x phi. So this is x, phi of A, x, y, phi of B, x. So this is phi tilde A, phi tilde B. And what is phi tilde 1? Well, this is, what is it? Y, phi of 1, x. But y, where does y live? It is somebody times phi of 1. And phi of 1 is idempotent because phi is a homomorphism and 1 is an idempotent. So this is the same as y. So this is yx, so this is p. Right? So if you have the homomorphism that satisfies what you want, then you can easily arrange that satisfies the commutativity of the diagram. You can easily arrange it so that it also sends one where you want it to send it, to be sent. And how does one prove part 2? Prove that you can find a homomorphism satisfying this. Okay, so I mean, so C of the class of E star, which is the same as C of the class of RE, will be the class of some idempotent, right? But for every E, we can choose PE, a BF idempotent, so that PF, PE, P prime equal to P prime PE equal to 0 if E is different from E prime. Why can we do this? Well, I mean, each of these, so choose so that the class of P is C of E star. Why can I do this? Well, because I am assuming that that is Pi, right? So if I have P1, Pn in idem BFR, then I do consider Qi equal to Si Pi Ti, then Qi is more phenomenal equivalent to Pi, and now Qj is 0 if I is not J. Why? Because Ti Sj is 0. Okay? So using these S's, I have a bunch of idempotent. I have any finite set of equivalence classes of idempotents, or very full idempotents if I want, because this will still be very full since it's more phenomenal equivalent to one that was very full by hypothesis. So I have any finite set of classes, or any finite sequence, not set, sequence of very full idempotents, of classes of idempotents, then I can find very full representatives of them which are orthogonal in the sense that the product is 0 using this. Even I have, so even if my sequence is this class, this class, this class, this class, always the same one, I can find orthogonal representatives of the same one. I mean, this will be orthogonal even if all the pi's are equal. Okay? So we can find such a thing. And now, because of CK2, so CK2, I will do the proof only in the case irregular to save, I mean, for simplicity. If it's not regular, it can be done too, but I want to be simple. So, so you take any graph, and this is equal to this in LE, right? And so and these are orthogonal idempotents. So this is this. And therefore, and this is the same. So if yeah, so for every vertex. So in particular, for every E, PE, whose class is the class of RE, is the sum of the classes of the PF such that the source of F is the range of E. Simply because Xi is a homomorphism, and the same equation holds in the original monoid. So we have this Xi. In here, the range of E is equal to the sum of the E stars. So the same should be true after applying C. Okay? So we have this. And because the PF are all orthogonal, this is the same as the class of the sum of the PF. So this guy and this guy, without the brackets, are Murray von Neumann equivalents. So we can find an XE and a Y and an XE in. So let me write the thing inside the bracket, call it sigma E. So I can find an XE in PE R sigma E and a YE in sigma E R PE, so that XE YE is PE and YE XE is sigma E. So I'm practically done. Now I have to say who phi is, and I define phi from LE to R by sending E to XE and E star to YE. What do I do with the vertices? Well, I use CK2. Every vertex is assumed to be regular, and so it is a sum of E stars. I know where to send the E's and the E stars, so I know where to send the B's. And you can check that the relations are satisfied. So that's how we lift it. Okay. So this is how we do the lifting. And now, well, so suppose, let me erase this. So now, suppose, and sorry, I will use my favorite letter for a thing I don't understand, which is Xi, right? A nasty thing. So I have my Xi here. And the evaluation of Xi is something here, which is what I previously called Xi. Then, by the surjectivity of this map we have just shown, this is evaluation of some phi in here. Okay, so if I do C minus the class of phi, then this will be the boundary of someone, right? So what I need to show is that for any class, let's call this U. For any U, phi plus boundary of U is some phi, is the class of this, is the class of some phi U, where phi U is still a homomorphism. Right? Because then I will show that the class of C is the class of some homomorphism, so I will show that this is onto. Right? And for this, I need to understand what on earth this map is. And yeah. And where does this map come from? Where does this map come from? Well, we had this triangle. And we homed this in KK on the right with R. So we get this exact sequence here. And the map partial comes from here. So it's a boundary map, which when you home, you go in the opposite direction. Home of L minus 1 to R is K1. And this is how you get that. Well, and where this come from? So this came from writing LE as a quotient of CE by some KE. This part gives us this part. But what do we know about the connecting map? It's mysterious. So mysterious. However, we can make the following observation. So, yeah. So suppose that E is essential, meaning that it has, so E is regular, and it has no sinks, no sources. So not only there are no vertices that do not emit edges, but also there are no vertices that do not receive edges. Then consider ET, come home, which is the same, is the graph with the same E1 and E0, but with two new maps, so that RT is S and ST is R. right? So you reverse the order of the arrows. That's what you do. Right. So, and now you have, so we have L E T. So this condition means that E essential, if and only if E and ET are both regular, because the sinks of E go to sources of ET, and the sources of E go to sinks of ET, right? So we assume that E is essential, and then we have here LET and 1 minus AE without the T, and then this is LET. And we can, if we want, we can tensor this with R. And we still have a triangle. And so if we write, and then we can take KKL, comma this. So all this is possible. And what we get is KH1 LET tensor R goes to home BFE K0 bar goes to 0. And here we get BF tilde of E tensor KH1 of R. So again, we take this triangle, we tensor it with R, that's still a triangle, we home it on the left with L, so that what the groups that appear are all KH groups. And if you work out the sequence that you get this. So you get this. And so we see that the two things that we have at the both ends are the same, right? And what is and yeah, why is this observation relevant? Because this guy, I just said, is a mystery. But this guy, I know where it comes from. It comes from this one. And this one, where it came from? Where did it come from? Well, this is CET goes to LET. So it comes from the projection map, which I understand what it is. So the question is, are they the same? Is this the same as this? And the answer is yes. And that's Poincaré duality. So so this goes as follows. Let me see here. Say is essential. And R and S are algebras. Then there is a natural isomorphism. R es tensor LET. Thus, tensor LE, and tensor LET are adjoint functors. Okay. Of course, I like to brag about every result that I proved, but this one is not a big source of bragging because, in fact, the sister algebra case is due to Kaminker and Putnam. And what I did was just check that the same proof goes through purely algebraically. Okay. So, yeah. And in particular, so set R equal to L. 1. Sorry. Here there's a 1. So you have to shift this. So in particular, what we get is KK LES equals KH1 of S tensor LET. And you check that the mystery map becomes the easy map. And using that, one can prove exactly that. And let me finish by explaining what this phi u is. So this goes as follows. So suppose that eb c equals eb phi, then there exists ue e in E1, so that ue lives in phi e star r phi e star is a unit. So this is an idempotent in R. This is the corner corresponding to the idempotent. This is a unitary ring with unit this guy. So it makes sense to say that some element in it is invertible, right? So that's what I mean by a unit, an invertible element. Okay. Okay. Such that phi u from LE to R, phi u of E is UE E, and phi u of E star is E UE E star UE. Sorry, phi of E and phi of E star UE inverse, and C is the class of phi u. Okay, so this is exactly what you get. And yeah, so, and the way one can prove this is I mean, in the paper with Diego, we have another proof that is gleaned from what Rordan does in his paper. But I found later on that using Poincaré duality, this is much simplified. And in any case, this is what you get. Yeah. So this argument shows the surjectivity. And this map, since M2 homotopic maps go to the same map here, then these factors modulo M2 homotopy. And you can further show that two maps go to the same, two very full homomorphisms go to the same K class if and only if, not only if and only if they're M2 homotopic, but one can get from one to the other using very specific constructions. So you have a unitar one, then you can compose it with some interior homomorphism. That's one thing you can do. And the second one is you can change phi by some phi u, so that all these UE are connected by a polynomial path with the identity. Right? So this is all you can do. In two or three of these changes at least, you must, so if phi and psi are here and they go to the same, then you can pass, then psi can be obtained from phi, replacing phi by some phi u, with u homotopic to the identity, or replacing phi by composing it with some adjoint, no, adjoint, no. What is it called? Inner automorphism. Right? So, well, that is all I wanted to say. Thank you.